Go. 4.4 concavity and points of inflection. So we're going to talk about concavity in the second derivative. So number one, the graph y equals f at x is concave up on some interval between a and b. Okay, so say a and b, in which the slopes of f at x are increasing. Okay, this is very, very different than an increase, than f at x increasing. This is the slopes would be increasing. Okay, on this interval, f double prime, so the second derivative exists, and the second derivative is greater than 0. Okay, the graph of the function is above the tangent at every point on the interval. So here's what happens, okay, if we're actually thinking about slopes and slopes increasing. So here's our curve, which is the blue. So now if I have this red slope here, oh, I should probably do red. One sec. Okay, if I have this red slope here, I could just estimate, and this is just making it up, okay, down 3 over 1, down 3 over 1, okay? So negative 1 over 3. No, negative 3 over 1. Okay? But if I were to have the next slope here, I'll do this one in green, okay? If you think about it, it would be down 1 over 2, down 1 over 2, down 1 over 2, just as an example, okay? So I would have down 1 over 2. Okay, if we think about our actual function and the slope increasing or decreasing, this number is actually increasing. So we're going from negative 3 to negative 1/2. And we know in regards to a number line, if you had 0, negative 1/2, this is going to be negative 3 over here. The more we move to the right on a number line, we're increasing. Okay? So that one's a little bit more difficult to see because the actual y values on f at x are decreasing, but the slope itself is increasing. Okay, that's the focus there. And now this one's going to be easy to see when we're going from a to b. I mean, this could be, I don't know, this could be the slope of 2, and then this could be the slope of, I don't know, 5, right? So this increasing one is very easy to see. This one that's more difficult. Okay, so be mindful of that. Now, the graph of f at x is concave down on some interval between a and b, in which the slopes are decreasing. Okay, but again, these are slopes that are decreasing. Okay, on this interval, the second derivative exists and the second derivative is less than 0. Okay, the graph of the function is below the tangent at every point on the interval. So if we had two tangent lines like this, okay, this is the easy one. This is the one that we can say, okay, well, maybe this is 3 over 1. So maybe the slope here is 3 and the slope here is 1 over 2 or something. 1 over 2. So we can see that that one's decreasing. That one's coming to a halt, okay? But the next one, this is the more difficult one. Okay, because you'd think that it's getting more and more steep, but you actually have to consider the numbers, okay? So here's the tangent. Let's just say negative 1 over 2. If we then have this tangent here, this would be negative 3 over 1, as an example, okay? And this is decreasing. This is getting into the negatives more. So it's a bigger negative number, therefore it is decreasing. So number 3, if y equals f at x has a critical point at x equals c, then the first derivative at c equals 0. Okay, we know that about critical points. We already talked about that, okay? Then the behavior of f at x equals c can be analyzed through the use of the second derivative test. Okay, so you want to highlight this second derivative test, and we can do that by analyzing the second derivative. So here's what the second derivative test tells us. The graph is concave up at that critical point, and that critical point x equals c is the location of a local minimum value of the function. Okay, is f double prime at c is greater than 0. Okay, if f double prime at c is greater than 0. So we're going to have a local minimum. That's from something else. If the second derivative at that critical point, okay, but remember the critical points are from the first derivative, okay, but if that is greater than 0. Okay, think when the second derivative is greater than 0, it's up. Okay, think like greater than is up, so it's concave up. Because it's concave up, again, minimum. Okay, and the second part of the second derivative test is if the graph is concave down at x equals c, the graph is concave down and x equals c is the location of the local minimum value of the function if f double prime at c is less than 0. So think less than 0 is down. Okay, so it's going to be concave down, and therefore it's going to be a maximum. Okay, and the third option, or the third situation that we're going to see is the second derivative equals 0. So the nature of the critical point cannot be determined without further work. Okay, number 4, a point of inflection occurs at c, comma, f at c on the graph of y equals f at x if the second derivative changes signs at x equals c. Okay, that is, the curve changes from concave down to concave up, or vice versa. Okay, so here would be like that point C, and on one side we can see it's almost wanting to do like a concave down, and then on the other side here it's wanting to do a concave up. Okay, so that would be a point of inflection. Okay, again, going down first, that'd be concave up, and then this would be concave down. So as long as that changes at that point is a point of inflection. Okay, and all points of inflection on the graph of f at x must occur either where the second derivative is 0 or where the second derivative is undefined. Okay. So here's our test for concavity. Okay, summed up. The second derivative must exist on an open interval I. Okay, the graph is concave up on that interval if the second derivative is greater than 0 for all values of x in that interval. Okay, that means it's increasing. The graph is concave down on that interval if the second derivative is less than 0 for all values of x in that interval, decreasing. Okay, here's the note. A point of inflection is a point on f at x where the function changes from concave up to concave down. Okay, specifically, f double prime at c equals either 0 or undefined. Okay, in our second derivative test, we're going to take the second derivative, and if it's greater than 0, we have a local min value. If it's less than 0, we have a local max value. And if it equals 0, then this test fails, and we have to use the first derivative test. So example 1, sketch the graph of x cubed minus 3x squared minus 9x plus 10. Okay, so we're going to start putting this all together. Okay, first of all, this is a polynomial. Okay, so we're not going to have to deal with, like, we can make a note if we want. So there's going to be no horizontal asymptote, vertical asymptote, or oblique asymptote. We don't have to worry about that. Okay, this is a polynomial. And we know that polynomials have the domain XER and YER for this one because the degree is 3. Okay, so we can hop right in to the critical points. So let's take the first derivative. Okay, so y prime equals 3x squared minus 6x minus 9. Okay, so let's find the critical points. So if we want, so find critical points. And we can label this first derivative. Okay, so to find the critical points, we go 0 equals 3x squared minus 6x minus 9. I'm going to go ahead and factor out a 3. We're left with x squared minus 2x minus 3. Okay, so what two numbers multiply to negative 3 and add to negative 2? Okay, negative 3 and 1. So we get 3 bracket x minus 3 bracket x plus 1. Okay, so our critical points occur at x equals 3 and at x equals negative 1. These are our critical points. Okay, so alongside this, I'm going to then do first derivative chart. So we're going to do f prime at x because we're going to take a look at the slope and see what the slope is doing between negative infinity and our first critical point, which is negative 1. Okay, negative 1 and our second critical point, which is 3, and then 3 and infinity. Okay, we want to know what's going on between those points. Okay, so our full derivative function is this right here. We have to make sure that every single component out of this is listed. So we have 3, x minus 3, and x plus 1. Okay, so choose a number between negative infinity and negative 1. I choose negative 2. Negative 1 and 3, choose 0. 3 and infinity, I'm going to choose 4. So 3 is never going to change. We can't sub anything into it. We don't have an x value. So all of these are going to be positive. 3 is always going to be positive. Now, negative 2 minus anything is going to be negative. 0 minus anything is going to be negative. 4 minus 3 is positive. Okay, negative 2 plus 1 is going to be negative. 0 plus 1 is positive. 4 plus anything is also positive. So we get positive, negative, positive. That means on this interval between negative infinity and negative 1, we're increasing, we're going to be decreasing, and then we're increasing again. So I want to note that this is the function that's increasing and decreasing because of simply the signs. We can say sine of f prime at x, okay, the sine of the slope, but this is not the slope is increasing or decreasing. It's not that. Okay, so that's first derivative. Now let's do the second derivative. Okay, so we had 3x squared minus 6x minus 9. So the second derivative here is 6x minus 6. So let's solve for when that equals 0. Okay, we bring this over, we get 6 equals 6x, divide both sides, we get x equals 1. Okay, so what this means is that we have a point of inflection at x equals 1. So what we want to do is determine the sign of the second derivative. Okay, so here's our second derivative chart. So we're going to start with interval. Okay, so we're going to go when x is less than 1, so negative infinity. We're going to have 1 here. Technically, it's x is less than 1. And then when x equals 1, so I'm not going to do these up here. Okay, when x equals 1, and then when x is greater than 1. Okay, and we have to sub it into f double prime at x. So f double prime at x, the thing is f double prime at x is just kind of one factor, right? It's 6x minus 6. Or we could break it down into 6 and then x minus 6, but let's just do 6x minus 6. So choose a number less than 1. So let's just choose 0. We're going to actually sub in x equals 1, and then we're going to choose the number greater than 1. So say 3 or 2. I always usually just do like the smallest number that I can get my hands on. Okay, so if we sub in 0 to 6x minus 6, we get a negative number. Okay, if we subbed in 1 to 6x minus 6, we actually get 0, and that's for a purpose there. Okay, and if we subbed in a bigger number than, so say 2, so 6 and 6 is 12, minus 6, we're going to get a positive number. So we can determine the concavity, okay, of this. And remember, if this, like this is our full f double prime function, but if this function was longer or more of a factor function where we have different pieces, we just list them like normal. Okay, it's just because it's like linear, like 6x minus 6, that we can just list the 1 and be okay with it. Okay, so the concavity for negative, it's down. It's concave down, which is going to look like this. At 0, there's no concavity. This is a point of inflection, right? So it could be like this. It could be like this here. Okay, and then for x is greater than 1, we have concave up. Okay. So now, finally, let's do the second derivative test. Okay, so our second derivative test, if you remember, we have to take our critical points from up here, which are 3 and negative 1, and we have to sub them into the second derivative. So y double prime at 3 is 6 times 3 minus 6. And we're also going to test y double prime at 1. So 6 times 1 minus 6. Okay, so what we get for this one is 18 minus 6, which is 12. And we can conclude that this f double prime at 3 is greater than 0. Therefore, this is a local minimum, okay, at 3 comma, and it would actually be 3 comma negative 17 if we plugged 3 into the original function up here. This one here, okay. And the second derivative test at f double or y double prime at 1, so 6 times 1 minus 6, we get 0. Oh, I'm sorry, this is negative 1. 6 times negative 1, which is negative 6 minus 6, we get negative 12. So f double prime at negative 1 is less than 0, right? This is a negative number. So therefore, for this point, we have a local max at negative 1 comma 15. Okay, and if we sub in this 1 for the point of inflection, okay, we can say that we have a point of inflection, and I'll put it over here with this, at 1 comma, and if we subbed it in, we get 1 comma negative 1. Okay, so let's go ahead and graph this. Okay, so I'm going to put the graph over here in, let's go black. Okay, so first derivative, critical points are 3 and negative 1. So at 3, we're going to have a turnaround point, and at negative 1, we're also going to have a turnaround point. Okay? Okay, so we're going to have that local max at negative 1 comma 15. So let's go ahead and plot a point there. We'll call that 15. And we're going to have a local min at 3 comma negative 17. Okay, so negative 17. Okay, what else can we read from our charts? So we're going to first be increasing until that -1, then we're going to decrease, then we're going to increase. So this gives us our like zigzag that we learned in advanced functions, okay? So we're going to be increasing to that maximum, and then between these, decreasing, and then increasing. So I hope that like with this, you get more of an appreciation with this -1 and this 3, that this, and like obviously negative infinity and infinity, but this being our number line, whereas that corresponds directly to what's happening here. Okay, the number line being the pretty much the x-axis, what's happening between, it's going up and then down and then up. Okay, we want to label our point of inflection, which is 1, -1. So I'll do it here, 1, I guess this will be our -1. That's fine. That's our point of inflection. Okay, and this is approximately halfway between like it going down, this graph going down and the graph going back up. Of course, it's not drawn to scale, so it's not exactly half, but it's approximately halfway between. And that point of inflection goes from concave down, which we can read from this chart, okay? Less than 1, so as soon as we have our point of inflection here, less than 1 is going to be concave down, and then greater than 1 is going to be concave up, okay? And right at 1 is going to be our point of inflection. Example 2, sketch the graph of f at x equals x to the 4. Okay, so I just want to kind of put this in the corner here. We know what this looks like. We know it looks like this. So we do this example because I really want to talk about what's going on here when that flattens out and what that looks like in regards to all of our testing. Okay, so first of all, this is a polynomial. Okay, so the domain is XER and the range is also XER, or sorry, YER. Okay, so let's go ahead and find the first derivative. Okay, we get 4x cubed. So find the critical points. We're going to solve when 0 equals 4x cubed. Okay, if you need to see the math behind this, you divide both sides by 4. We get 0 equals x cubed, and then you can cube root it. So 0 equals x. Okay, so we have a critical point at 0, 0. Okay, so as soon as you do the critical points, let's do the chart based on critical points. Okay, so this is just going to be negative infinity, 0, and infinity. Okay, and then down the side, we're just going to have x to the 4, and that's it. So if we have any negative number, say -1, anything raised to the 4 is going to be positive. And then any negative or positive number, let's just say 1 raised to the 4 is also going to be positive. So the slope, so let's put the equation for the slope in here, which is 4x cubed. So if I test -1 and 1, I'm going to get a negative number and then I'm going to get a positive number. So we're decreasing in the first between negative infinity and 0, and then we're going to be increasing because this is the sign of f prime at x. Okay, now let's do the second derivative. So that's the first derivative. Second derivative, y double prime equals, we're going to have 12x squared. So when does 12x squared equal 0? Because then we can find points of inflection. Okay, so we get 0 equals x squared, and then obviously if you root both of these, you get 0 equals x. So there's a point of inflection, okay, at 0, 0, and we should say possible. Okay, so we don't know if it's a point of inflection yet. We have to test it in our chart. So let's take a look at our chart. Okay, so we'll do interval on the top. Okay. And we're going to have, because that's a point of inflection or a possible point of inflection, 0, 0, we're going to do below that. So when x is less than 0, okay? We want when x equals 0, and then we also want when x is greater than 0, okay, on each side of that point of inflection. And if we have 2 points of inflection, we have to do it on each side of each point of inflection, as well as at those possible points of inflection. So our f double prime at x, which is 12x squared, let's go ahead and sub in a number. So we're going to sub in -1. Okay, we get positive. When we sub in 0, we do get 0. And then we sub in, say, 1, and we get a positive again. Okay, so what can we conclude? And I always underline this because this right here could be 3 or 4 lines, depending on how big the polynomial is. So concavity. Okay, if it's positive, we're concave up, which means it's going to look like this. Okay, I'm going to skip that one. Positive again, we have concave up, which means it's going to look like this. Okay, so here's the thing. For concavity, for 0, we actually don't know what's going on, but until we assess what's going on the left and the right. So on the left, it's positive. On the right, it's positive. Therefore, this is not a point of inflection. Okay, and we'll make a note here. 0, 0 is not a POI, point of inflection, because f double prime at x does not change sign. At x equals 0. So if you think about it, we're not going from concave up to concave down or concave down to concave up, which is, in our note, the definition of what a point of inflection is. Okay, so let's do the second derivative test now. Okay, so we're going to take y double prime. So let's just call it x double prime just for nice notation. And we're going to sub in the original critical point, which is 0. Okay, and we get 0. Okay, so 0, 0 is going to be something. So if we take a look at f prime at x, okay, so the slope is less than 0 when x is less than 0, and the slope is greater than 0 when x is greater than 0. So therefore, 0, 0 from here is going to be an absolute minimum. So essentially what we would have done there is we would have went up to f prime, right? This is f prime. And because we're going down first and then up, we get that minimum. So we can take a look on either side of that 0. Okay, because 0 is both a critical point and a possible point of inflection. We had to determine which one it is. So we have to look at both charts. Okay, and then finally, we can go ahead and graph this. So let's graph our x and y axis. Okay, we know that we go through 0, 0, that's possible point of inflection, but it's not. We know on the left side, we're going down. Okay, we're decreasing. The slope is decreasing. And then on the right side, we're going up. Okay, so that's our y equals x to the 4 graph. Okay, and then we can also check our concavity, concave up, on the entire domain. Example 3, sketch the graph of the function f at x equals x to the 1/3. Okay, so first we're going to take the derivative. So we're going to go f prime at x equals, it's thicker, okay, actually I'm going to rewrite, no, that's good. 1/3, because we're going to bring this down in front, x, and then we're going to subtract 1 from the exponent, so -2/3. Okay. Another way of writing this is f prime at x equals 1 over 3, right? 1 over 3. And then since x is to the negative 2 over 3, we can write this as a positive exponent and put this in the denominator. So x to the 2 over 3. Okay, so what we're going to do first is find the critical points. Okay, we're going to equate the derivative to 0. So 0 equals 1 over 3x to the 2/3. Okay, so when does 0 equal 1 over 3x to the 2/3? Well, if we cross multiplied this denominator up, we're going to get 0 equals 1. Well, we know that 0 cannot equal 1, and therefore there's no critical number. There's no critical number, there's no critical points. So then we can say, so to determine the behavior of f prime at x as x approaches infinity, or sorry, x approaches 0, f prime at x has to be greater than 0 for all values. Of like when x does not equal 0, and the denominator of f prime at x is 0 when x equals. So if you think about it, the limit as x approaches 0 of f at x, it approaches positive infinity. So therefore, we're going to have a vertical tangent when x equals 0. Okay, and just a note, f at x is increasing on x is less than 0 and on x is greater than 0. So there's not going to be a max and min. Therefore, no max or min. Okay, so now let's do the second derivative. So we come up here and we know that the first derivative is 1/3 x to the negative 2/3. Okay, so the second derivative is going to be, if we bring down negative 2 over 3, we are going to get negative 2 over 9 x, and then we subtract 1, so that's negative 5 over 3. Okay, to rewrite this as a fraction, if we want, we get negative 2 over 9 x to the 5 over 3. So taking a look at x to the 5 over 3, if we think about x to the 5 over 3, when we plug in any number greater than 0, x to the 5 over 3 is also going to be greater than 0. Okay, and x to the 5 over 3 is going to be less than 0 if we plug in a number less than 0. So here is our chart for concavity. Interval. Okay, so the intervals are going to be when x is less than 0, when x equals 0, because we have to test that if it's a point of inflection, and then when x is greater than 0. So let's test these numbers in the second derivative. So x is less than 0. When x is less than 0, it's going to be negative. So negative over negative, I'm getting a positive. When we sub in 0, this does not exist because negative 2 over 0 does not exist. And now if x is greater than 0, which is this situation here, then x is going to be greater than 0. So this is going to be a positive over a negative, or sorry, a negative over a positive, which is going to give us negative. So concavity. This is concave up. You can put CU, so it's going to look like this. This is not a point of inflection. Okay, so let me go back on this. Okay, let's do when x is greater than 0. This is concave down, so it's going to look like this. And because we're going from concave up to concave down, this is actually still a point of inflection. It's just going to look like this. From concave up to concave down. So you can write yourself a little note. Therefore, the point of inflection can exist even if f prime at 0 and f double prime at 0 does not exist. Okay, and how that graph will look. Is like this. Example 4, determine any points of inflection on this graph, f at x equals 1 over x squared plus 3. Okay, so first I'm going to rewrite f at x as x squared plus 3. I'm going to bring that bracket to the top into the numerator, and it's going to be to the negative 1. I'm not going to write the negative 1 in front, it's redundant. So let's find f prime at x first. Okay, we bring down the negative 1. Okay, and it's x squared plus 3. We subtract 1 from there, we get negative 2. But then we have to do the chain rule. The chain rule is, what's the derivative of x squared plus 3? We get 2x. Okay, so let's leave the negative and the 2x in the numerator. And let's bring this bracket, x squared plus 3, to the denominator so that this negative 2 in the exponent becomes a 2. And now we can find the critical points. Okay, so this is f prime at x. Okay, to find the critical points, you put 0 into f at x. And we get 0 equals negative 2x over x squared plus 3 squared. So if we were to cross multiply up, that denominator goes to 0. So now we have 0 equals negative 2x. And if you really need to do the math behind it, divide both sides by negative 2, and we get x equals 0. Okay, so that's going to be the critical point. Okay, so now let's find f double prime. So f prime at x, let's take this one here because everything's in the numerator. So we have negative 2x bracket x squared plus 3 to the negative 2. Okay, so this is one term, this is another term. So this is u, this is v. Because this is product rule, we're going to go u prime v plus uv prime. Okay, so f double prime at x equals derivative of u, which is negative 2, times v as it is, x squared plus 3 to the negative 2, plus u as it is, negative 2x, and then v prime. So we're going to bring down this negative 2. We're going to write x squared plus 3. Okay, subtract 1 from there is negative 3. And then multiply that chain rule by the derivative of the inside, which is 2x. Okay, we're not able to really work with this. It's too difficult. We need this in fully factored form. So a lot of this is just going to be algebra. So let's write this first term as it is. Okay, so negative 2x squared plus 3 to the negative 2. Now, when we go over here, I'm going to start collecting. Okay, what is negative 2x times negative 2 times 2x? 2 times 2 is 4, 4 times 4 is 8. I get positive 8x squared. Okay, so this is just making it look a little bit differently. We're not taking any derivatives. Okay, we're just simplifying. And then we write x squared plus 3 to the negative 3. So what we want to do is we want to factor out the biggest term out of the first term here and the second term here. We can factor out a negative 2 out of each of these terms. We can also factor out an x squared plus 3. And the rule is always take the lower exponent. So what's the lower exponent, negative 2 or negative 3? Well, it's negative 3. That's a smaller number. So our common factor is negative 2, x squared plus 3 to the negative 3. And then let's do what's left over. So those cancel out. Those cancel out to a 1 on the top. So we have x squared plus 3 in the numerator. Then those cancel out. And then 8 divided by negative 2 is negative 4x squared. So we have f double prime at x equals negative 2, x squared plus 3 to the negative 3. And then x squared minus 4x squared, we're going to get negative 3x squared, and then plus 3. Okay, I'm going to leave this. We could pull out a negative 3. Okay, let's pull out a negative 3. So finally, f double prime at x, we're going to multiply this negative 3 by this negative 2 in front. Okay, so we get 6, x squared plus 3 to the negative 3, and then we have x squared minus 1. Okay, even more factoring. This x squared minus 1 is a difference of squares. So let's go ahead and do difference of squares for that. So I'm going to write these first two terms as they are. 6 x squared plus 3 to the negative 3. And then we have x plus 1, x minus 1. Okay, this is going to be fully factored. Okay, so to find possible points of inflection, what we want to do is we want to equate this to 0. And that means that each one of these factors, we want to find when this, we have to do that because of the negative 3. When each one of these factors equals 0. Okay, so when we think about this, we think about this term here being in the denominator, 1 over x squared plus 3 to the 3 equals 0. So when we cross multiply, we get 1 equals 0. Okay, and we know that 1 can't equal 0, so there's no possible point of inflection there. Bring this over, we get x equals negative 1, and then bring this negative 1 over, we get x equals 1. Okay, so these two here are going to be possible points of inflection. And now we have to set up the chart to actually test this. So let's set up the interval. Okay, so x is less than negative 1, x equals negative 1. And then x is going to be between negative 1 and 1, x equals 1, and we're going to have x is greater than 1. Okay, we want f double prime at x sign. Sign, and then we're going to conclude the concavity. Okay, so when x is less than negative 1, so let's say kind of like a negative 2 or beyond, okay, we have to take a look at f double prime. So 6 is going to be positive. Negative squared plus anything is going to be positive. 1 over a positive number is going to be positive. X, so negative 2 plus 1 is going to be negative. And then negative 2 minus 1 is also going to be negative. So this is going to be positive. Okay, x equals negative 1. If we sub that into x plus 1, we're going to get 0. Okay, a number between negative 1 and 1, we get, let's test 0. So 6 is going to be positive. 1 over 3 is going to be positive. 0 plus 1 is positive. 0 minus 1 is negative. Okay, x equals 1. When we sub that into 1 minus 1, it's going to be 0. And then x is greater than 1, say we're going to sub in 2. 6 is positive. 4 plus 3 is going to be positive. 2 plus 1 is going to be positive, and then 2 minus 1 is going to be positive. So that's going to be positive. So the concavity here is going to be concave up. This is going to be a point of, oh, wait, we don't know if this is going to be a point of inflection yet. This one's concave down. It's going to look like this. And then this positive is going to be concave up as well. Okay, so going from up to down, this is a point of inflection. And going from down to up, this is also a point of inflection. Okay, what does this mean? So if we think about the x and y axis like this, or the x and the f at x axis, whichever one. Okay, point of inflection is going to be at negative 1. So that's going to be a point of inflection. And 1 is going to be a point of inflection. If we actually want these values here, we can sub in f at negative 1 and then f at 1. We also want to sub in this critical point, f at 0, but from the original. So from the original, which is 1 over x squared plus 3. Okay, this is going to be 1/3, so 0 and 1/3. If we have negative 1, this is 1/4. If we have 1, this is 1/4. So this height here will be 1/4, and then 0 and 1/3 will be here. Okay, and then on the interval from x is less than 1, it's concave up. So it's going to be like this. Negative 1 to 1, it's concave down, so it's going to look like this. And then greater than 1 is going to be concave up again. So it's going to look like this.